Morning, everybody. It should be Monday morning right about now, and we're going to start. I hope you had a great weekend. I hope you had a great weekend. Took some time to be with your family and relax and have fun. Today, we're going to dive right into solving some trig equations. I'm calling this Solving Trig Equations Part 1 because there's going to be a second lesson about solving trig equations. Instead of just going over homework problems and stuff, what I'm going to do today is actually try and teach a lesson about trig equations. There's a couple things to keep in mind when we're solving trig equations, and I wrote them right here. A couple things to keep in mind. We're going to isolate the trig function. We're going to get the trig function by itself, and then we're going to have to think in our head like, okay, if the sine of the angle equals 1/2, then what does that make the angle? That's called using the inverse trig functions. And when we get hard ones, we'll use our calculator. But for now, they're not going to be very hard. We can think our way through these. Okay, so in order to get the trig function by itself, we're going to have to add or subtract stuff to both sides, or multiply both sides by a number, or divide both sides by a number, just like if we were trying to get a variable by itself. Also, we're going to have to factor and then use zero product property sometimes. Today, the last example we're going to do will have a zero product property in it, but it's not really, we don't have to really factor. I think it's the second to last example, actually. We don't have to actually factor because it's already factored for us. But later on, we will do those. And the last thing there, I made a little typo when I was writing that. The last thing, trig equations, they're going to have many answers or many solutions. And we'll talk about why that is in just 1 second, all right? So here we go. I'm going to advance the slide now. I'm going to advance the smartboard now. I'm going to advance it like that. All right, so you asked the question just now in your head, I think I heard somebody say, why would a trig equation have many answers instead of just one answer? Here's what we have to do. Think about this. If we get to a point, say, sine of x equals root 3 over 2, we have to think in our head, what angle x would have a sine of root 3 over 2? All right, here we go. Sine is root 3 over 2. Sine goes with y. Root 3 over 2 is the big one compared to 1/2. So that means it's going to be the higher one. And we're going to talk in radians, okay? And the higher one is pi over 3. So x would be equal to pi over 3. And we might go, okay, bingo bongo, done. But the problem is when we think of an angle whose sine is root 3 over 2, pi over 3 is the one in the first quadrant. So pi over 3 is like over here, pi over 3. But the angle with the same reference angle over here in the second quadrant, that would also have a sine of root 3 over 2. And that one is 2 pi over 3. That one's got a sine, that one's also got a sine of root 3 over 2. Okay, we got two answers. That's cool. Well, if the problem said, solve the equation for all values between 0 and 2 pi, and a lot of times they say that. If it said that, then yeah, we would be finished. We'd have these two solutions. But a lot of times, it doesn't restrict us to 0 to 2 pi, and so we got to figure out all the values of x that have a sine of root 3 over 2. Well, if I were to add 2 pi to pi over 3, if I added 2 pi to it, that would be equal to 7 pi over 3. You see, I added 6 pi over 3 to pi over 3. Okay, so that sine, the sine of 7 pi over 3, would also be, because it would be like, whoop, right there again, would also be root 3 over 2. And if I added 2 pi to 2 pi over 3, if I added 2 pi to 2 pi over 3, I would get 8 pi over 3. And so we'd be like, woo, woo, there, okay? And then if we did it again, and if we did it again, and if we did it again, and if we did it again. So, for the solutions for this guy, we would say pi over 3 plus 2n pi, 2n pi, and 2 pi over 3 plus 2n pi. That would be all the solutions. And that's going to be, we'll get the hang of that. We'll get the hang of that. It's kind of tricky at first, but we'll get the hang of it. Okay. We'll get the hang of it, I promise. All right, we're going to do some examples now, and they're going to get like a little bit harder as we go. All right, I'm going to leave that there. That's my scratch paper. I'm going to take this guy down. I'm going to advance the slide. Advancing the smartboard to example 1. Example 1. We got 2 cosine of x minus 1 equals 0. Remember, as we get started on these guys, what we want to do is get that cosine of x by itself. We're going to isolate cosine of x. So if we do some fancy algebra on this guy, we're going to add 1 to both sides. And we're going to get 2 cosine of x equals 1. And then we're going to divide both sides by 2. And we get cosine of x equals 1/2. Cosine of x equals 1/2. Now we have to figure out when is the cosine of x equal to 1/2. Well, this one's kind of like the one we just did a minute ago, where the sine of x was root 3 over 2. At least in the first quadrant is going to be the same, because if we think about cosine is 1/2. 1/2 goes with x. So that's going to be the x coordinates 1/2 in the first quadrant. That means it's going to be high and close, so it's going to be the steep one, and that's pi over 3. And so we could say x must be pi over 3. That's cool. But then where else is cosine positive? Which other quadrant is cosine positive? Can we think about that for a minute? We have our 4 quadrants. Where is cosine positive besides the first quadrant? Is it positive in the second quadrant? No, because it's left of the y-axis. So it's the 4th quadrant. The 4th quadrant cosine is also positive. So what would the angle whose reference angle is pi over 3 that's in the 4th quadrant be? Right, 5 pi over 3. So good. So x would be 5 pi over 3 as well. Okay? But we also have to account for all the angles wrapping around the unit circle. Wrappy, wrappy, wrappy. So when we wrap around the unit circle, we add 2 pi. So we say x equals pi over 3 plus 2n, I did it again, plus 2n pi, and x equals 5 pi over 3 plus 2n pi. The 2n pi, that takes care of revolutions around the unit circle. So the n just means a multiple. And we always assume n is an integer. So it's like a 1 or 2 or 3 or 4 or 5 or a -1 or 2, a -2, a -3, -4, etc. So here's your solutions for this equation. It looks like a very simple equation, and it is a very simple equation, but the solutions are wacky, okay? Now again, if they told us just to restrict our answers to between 0 and 2 pi, we'd get those 2 answers there. But since it doesn't say that, we're wrapping all the way around. We're having all the multiples of, we're adding multiples of 2 pi to our solutions. All right, second example. This time we got a nasty secant in there instead of just a happy cosine. We got a nasty secant. So we're gonna get that secant. You know what? We'll probably get the secant squared by itself first. We'll get the secant squared by itself, and then we're probably gonna change it to cosine. Flip it, because it's a little bit easier. So here we go. We're gonna add 4. I'm gonna use red this time. I like red. We're gonna add 4 to both sides. And we got 3 secant squared x equals 4. Then we're going to divide both sides by 3. And we got secant squared x equals 4/3. Yeah, we can probably keep going. So let's do the square root of both sides. Secant of x equals plus or minus 2 over the square root of 3. Now, what I would normally do if I get to a situation, no, I shouldn't say normally. If I get to a situation like this, where I'm solving and I get a square root in the bottom, I would probably go through the process of rationalizing the denominator. However, I got the secant of x equals 2 over root 3. So I know I'm going to flip it. And I'm going to say, well, if the secant equals 2 over root 3, then the cosine equals plus or minus root 3 over 2. So the cosine of x equals plus or minus root 3 over 2. Okay, so now I'm in a similar situation as I was on example 1, where I have a value for the cosine. And I got to think. Cosine is root 3 over 2. That means it's the lower one because of the two angles. It's the lower one because the cosine is going to be bigger than the sine. So, see, root 3 over 2, that makes it pi over 6 is the lower one. So I'm going to say x is pi over 6. But again, I got to account for wrapping around the unit circle. So x equals pi over 6 plus 2n pi. But x could also be, where else is root 3 over 2 the cosine? Positive. Oh, in the fourth quadrant. So I could say fourth quadrant would be like 11 pi over 6 plus 2n pi. Oh, what's that, you say? What's that? You bring up a good point. It's plus or minus. So I also have the values of x where the cosine is negative root 3 over 2, which would be which two quadrants is it negative? Which two quadrants? Right, the second and the third quadrant. Very good. So the second and third quadrant. So now I've got, instead of pi over 6 plus 2n pi and 11 pi over 6 plus 2n pi, I've also got the corresponding value in the second quadrant, which is, right, 5 pi over 6. 5 pi over 6. I'm sorry if you can't read this very well. It says 5 pi over 6 plus 2n pi. And then the corresponding value in the third quadrant, 7 pi over 6. Good, I'm going to have a struggle here. Got it right here. 7 pi over 6 plus 2n pi. All right, now what I'm going to do real quick is flip this over to say what all the answers are. All right, I'm going to get a piece of tape. That's what I'm going to do, so I can have a little more space. All right, that's pretty fancy there, huh? A little MacGyver situation. All right, so we got pi over 6. We got 5 pi over 6. We got 7 pi over 6. And we got 11 pi over 6. But remember, we had those plus 2n pi's? Okay, the plus 2n pi, what that does is it takes care of all the corresponding angles that are exactly one multiple of a unit circle away. But look closely at these four solutions. How far apart is pi over 6 and 7 pi over 6? So pi over 6 is like here, and 7 pi over 6 is like, see on the unit circle, it's here. Here. They're exactly half of the unit circle away from each other. They're pi units away from each other. So to get from here to here, it's just pi. And to get from here back around to 13 pi over 6 would be add another pi. So instead of having to write pi over 6 plus 2n pi and 7 pi over 6 plus 2n pi, we can take care of all those solutions by just saying pi over 6 plus n pi. And that will then hit me on the pi's over 6's and the 7 pi's over 6's as we go around the unit circle. Same idea holds for 5 pi over 6 and 11 pi over 6. If I add pi to 5 pi over 6, I get 11 pi over 6. So my solutions to this one would be pi over 6 plus n pi and 5 pi over 6 plus n pi. I wouldn't have to mention these because these are included over here. That's kind of a hard idea, but we'll see more examples like that in the assignment, especially coming up, as well as the examples we'll continue to go over. All right, so I'm going to advance the smartboard now. and we're on example 3. Now this is the one I referred to a little while ago when I said we're not going to have to factor, but we'll use a zero product property. This one's already factored. I wouldn't have to do any factoring. But let me show you what it would have looked like if it wasn't already factored. The original problem might have said 3 tangent to the 4th x minus 1 minus 9 minus 10 tangent squared x plus 3 equals 0. If it said that, we would have had to factor this into here. But right now, we're going to practice getting from here to the answer instead of having to worry about this. So if I use a zero product property, because I have two numbers, one number, two numbers, multiplying together to give me 0, then if I use a zero product property, I know one of those numbers must be 0. So I got those two equations. If I solve these two equations, I'm going to do it kind of quickly. I'll have the tangent squared equals 1/3, or the tangent squared equals 3. So this one would be tangent of x equals plus or minus root 3 over 3. And this one would be tangent of x equals plus or minus root 3. Okay, now the solutions for this one, okay, I gotta think. Again, I gotta think. I'm always thinking. I gotta go, okay. I can picture that chart that we filled out with like 72 or 68, I don't know how many boxes there were on there. And I gotta remember, when is the tangent root 3 over 3? I gotta, okay. The tangent's root 3 over 3, I remember this now, when the sine's 1/2 and the cosine is root 3 over 2. That's how you get root 3 over 3. So when is the sine 1/2? 30 degrees, but we're talking in radians. Sine is 1/2 at pi over 6. Good. So we've got plus or minus. So I'm going to have x equals pi over 6. Okay. And then where else is the tangent going to be plus or minus root 3 over 3? All the way around the unit circle. Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So that's pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So let's look at these, how these four compare. These are exactly pi away from each other. These are pi away from each other. So I can get these two and these two separately. So I'll get pi over 6 plus n pi. I got 5 pi over 6 plus n pi. So those are the solutions for this half. Now I got solutions for this half. Well, when's the tangent equal to root 3? Think about sine over cosine. So this time the sine would be the bigger one. The sine would be root 3 over 2. So the sine is root 3 over 2, and the sine is root 3 over 2 at the higher one, and the higher one is pi over 3. So our solutions for this side would be x equals, okay, pi over 3, and every pi over 3, because it's plus or minus. So every single pi over 3. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. I almost wrote on the wall. I'd be in trouble if I did that. Okay, so these two are pi away from each other, and these two are pi away from each other. So we could write our solutions as pi over 3 plus n pi, and 2 pi over 3 plus n pi. I only got to mention these. I have all of my solutions. I'm going to mention this stuff. So you're probably thinking, wait a minute, I thought we were supposed to add 2n pi. Well, we are, but we don't have to list all 4 of them and add 2n pi. If we list 2 of them and add n pi, then we'll get it. But for an equation like this one actually has 4 different answers that all have plus n pi in them. They have all 4 different answers that all have plus n pi. Now, if the problem said restrict your answers to between 0 and 2 pi, you'd only have a total of 8 answers. You'd have 1, 2, 3, 4, 5, 6, 7, 8. But this directions don't say that. This one says find all the solutions. Okay? Last one. Last example. This one's actually pretty quick. All right. This one's kind of weird. There's a couple ways we could do this. There's like a really super duper easy way, and then there's one that would take longer. The one that would take longer would be to like substitute in like 1 minus cosine squared for sine squared. We could do it that way. We absolutely could do it that way. But we could also do it this next way. This next way is pretty cool. What we're going to do is divide both sides by cosine squared. Change colors. Divide both sides by cosine squared. Woo, woo. And we get, what's sine squared divided by cosine squared? Right, it's tangent squared. You guys are so smart. So this is tangent squared of x equals 3. That means that tangent of x equals plus or minus the square root of 3. Aha! So we just did one like this just a second ago. If tangent x equals plus or minus the square root of 3, that means x is going to be anywhere where the sine is root 3 over 2. Root 3 over 2 that's the sign of the higher one, and the higher one is pi over 3. That's plus or minus. So we're going to get x equals pi over 3 plus n pi, or it equals 2 pi over 3 plus n pi. Those are our solutions for that guy. And for the same exact way of doing it as we did the previous one, okay, where we had this exact step. All right, so now we're going to do a quick summary. All right. So we're going to, when we're solving trig equations, we're going to get the trig function by itself. We're going to isolate the trig function. That's the first thing we do. Then we have to think. All right, I need an angle whose sine is, or an angle whose cosine is. Picture the unit circle. And then we have to think, okay, how are we going to get all of the values around the unit circle that meet that qualification? And do we have to add n pi and 2n pi to it? Or is it restricted from 0 to 2 pi? Well, for this homework set, for tonight's assignment, which is like 12 through 24 even on page 482, for that assignment, they're all not restricted to 0 to 2 pi. So there you have to do that plus n pi or plus 2n pi. All right, well, I hope you guys enjoy this homework assignment. It's going to be a lot of fun. You're gonna have a great time doing it. And signing off from my basement. See ya.